Okay, hi everybody. I'm Jay. I'm Jay Mireles James. This is work about computer-assisted proofs for collision and near-collision orbits and the circular restricted three-body problem. It's joint work with Maciej, Capinski, and Shane Kepley. It's a real pleasure to be involved with the workshop. So let me go ahead and jump right in. I want to start by just explaining a little bit what is this circular restricted three-body problem. So this is a version of the three-body problem where you imagine that you have two massive bodies, M1, which is maybe the larger mass, M2, which is the smaller mass. They're orbiting their center of mass on circular orbits. And you kind of leave these bodies alone and just let them continue on those circular orbits. Now, you consider the dynamics of a massless particle, like maybe a comet or a small moon or a man-made satellite that is influenced by the gravitational field of these two large primary bodies. Okay, but the massless particle will not influence these bodies. They'll continue on their circular motion. So because of this, when you change to rotating coordinates, you change to a rotating frame that rotates with the frequency of these large primaries, you obtain an autonomous set of differential equations for the massless particle. Okay, and that's the restricted part, right? You're restricting the motion of these two large bodies and studying the free motion of this very small comet or satellite. Now, this is an interesting problem for certain kinds of orbit design, say missions from the Earth to the Moon or Sun, Jupiter, and so on. But it's also interesting mathematically because the full three-body problem is at least as complicated as this restricted problem, right? So if you can prove something complicated happens in this restricted problem, you know you have complicated dynamics in the full three-body problem. Okay, so the equations of motion are basically just to write down Newton's laws, where you, so second-order differential equations, F equals ma, where the force is given by partial derivatives of this gravitational potential. However, because we've moved to rotating coordinates, we have these kind of Coriolis terms, the minus 2y prime and 2x prime in the equations. If we play the usual trick of introducing x prime and y prime as their own variables, we can write this as a system of four first-order equations. So basically now we're just studying an autonomous vector field. And now it's clear that the dimension of the system is really a four-dimensional problem. However, it has a conserved energy-like quantity called the Jacobi integral. So I'll usually write E for this unless we fix a value of it, and then I'll refer to the value as C. Okay, so it's a 4D vector field, but the actual dynamics of any particular orbit live in these 3D level sets. Okay, so here's a example of a numerical integration of an orbit at a particular energy level for this system. And one of the things you can see is that it looks very complicated, okay? So it's not so easy to understand the dynamics of the system. So as usual, you kind of want to start with simple things. You know, where are the equilibrium points? Periodic orbits, say, in this energy level. Are there invariant tori, perhaps? Heteroclinic and homoclinic connections, maybe between equilibria or periodic orbits or tori, or connecting those various types of invariant objects. And because of the possibility, because this vector field has singularities at the locations of the primary bodies, it's possible to have collisions. So collision means going to a singularity in finite time, forward time, or we'll refer to an ejection as basically a collision in backward time. So it's as if you're ejected out of a singularity. So these collisions and ejections, of course, make the phase space more complicated than it might other be. There are maybe lots and lots of orbits that only exist for a finite amount of time and then whose velocities go to infinity. in finite time. But those are exactly the orbits I'd like to study today. So we want to do computer-assisted proof with orbits whose velocities go to infinity in finite time. Initially that maybe seems kind of unclear how you would do computer-assisted proofs precisely involving orbits where this vector field stops making sense, right? Precisely approaching the singularities of this vector field. Well, there's a classical technique that allows you to do this. Though what we use in this work is Levi-Civitta regularization. So let me say a few words about that. Now you can regularize at the large primary or at the smaller primary body, but the discussion is more or less the same in those two cases. So I'm going to focus for a minute on the larger primary. So here are our equations again. The idea behind Levi-Civitta regularization is, first of all, and this is absolutely essential, is that you need to fix some value of the Jacobi constant, some value c that you're going to work in. So you can only regularize the collisions one energy level at a time. Okay. Once you've fixed your energy, you define a complex variable. Z is x plus iy, and now new complex variable w, okay? And w is defined by this w squared plus mu is equal to z. So what you can see is if w is equal to 0, then you're basically at the collision with the large primary. You have x equal mu and y equals 0, because y is the imaginary part and mu is real. Okay, so that's a new coordinate. You also need to rescale time according to this rule. You can work out then your new velocities in terms of your old velocities are given by this transformation. And if you plug these new variables and this new rescaling of time into the equations of motion for the original restricted three-body problem given here, it's a lengthy calculation, but you obtain a new vector field, which is regularized at its origin. Now remember, the origin for W is maps to the collision in the original coordinates. So let me show you the formulas. Here's our original circular restricted three-body problem. Okay, you can see, for example, that if x equals mu and y equals 0, we have a singularity in this system. Okay, but the regularization at the large primary is this vector field with this energy. And here, if you look at what I call x hat equals 0 and y hat equals 0, you see that the denominator in this nonlinear term is just fine. You actually get square root of 1 is just 1 in the denominator. So there's absolutely no problem being at x hat, y hat equals 0 in these coordinates, which is the point that maps to collision in the original coordinates. Now, because of the squaring, there's like a double cover with these coordinates, but this is not really a problem. It's just something we need to be aware of. And we can do the same thing at the other primary, and I can write the formulas for this. Again, the formulas aren't going to be so important here. What's really important is that this can be done. There is some transformation that takes us from these regularized coordinates to the original coordinates and back, and we can do this at each of the bodies. Okay, so here's the regularization at the small primary. And the transformations that take us back and forth are these, okay? And these are locally diffeomorphisms. So globally, this is a double cover, but at any given point, you have a nice derivative here. Okay, so again, this is like a lot of formulas, but somehow the main point of this slide is just that these different coordinates and these different vector fields exist, and that this is a way to regularize collisions. Now, I want to say a few things about the actual collision sets, because this is really important when we're going to try to study these things numerically. First of all, as I mentioned before, you have to choose an energy level in your original problem that you want to work at and regularize at. And you can see here, this is my regularization, my regularized vector field at the large primary. That C, that value of the Jacobi constant that you decided to work at, appears as a parameter in your regularized vector field. And the coordinate transform is constructed in such a way that the energy level set associated with C in the original coordinates is mapped to the zero energy level in the regularized coordinates. So only the zero energy level is physically meaningful in the regularized system. So, and then the energy that you chose becomes a parameter in that system. Okay. The transformations, these Levi-Civitta transformations, again, it's very important that they're going to take, they automatically enforce this. They're going to take the energy level set C in the original coordinates to the energy level set 0 in the regularized coordinates and vice versa. Okay? So let's try to actually look at the set of collisions. So in the regularized coordinates, you're at a collision if you're at the origin. Okay? Remember W equals 0. That was the point that gets mapped to the collision back in the original problem. So, but you're also the only physically meaningful energy level is 0. So let's take the energy in the regularized system, set it equal to 0, and then suppose we're at collision. Okay, so now x equals 0, x hat equals 0, y hat equals 0. Well, then almost all of these terms completely disappear. Okay, and all we're left with is the minus q tilde squared minus p tilde squared is equal to a constant, where that mu is the mass ratio of the system. So, if I isolate the p and q, what I can see is that the set of collisions, it's actually a circle. I'm at 0 in the positions, but then I have a circle of velocities. Okay, so we know precisely what are the orbits in the regularized coordinate systems that correspond to collisions back in the original coordinates. In fact, we can just parameterize this, right? We can write down here just a simple parameterization of this circle in the regularized coordinates. Okay, so what I'm going to be interested in first are orbits that are ejected from one primary and that collide with another primary. So let's define these tubes, actually. So take the circle, parameterized by p, and let's flow that backwards for a time t. Well, that means any point on that cylinder is a point that collides in forward time. So we call this the collision cylinder associated with the time t. And then likewise, we have an ejection cylinder associated with taking the collision circle and flowing it forward. So those are things that in backward time would have an ejection in time t. So so these are cylinders. You can think of them as 2D manifolds in a 3D energy level. Okay, so if you think of the phase space as being three-dimensional, a pair of two-dimensional manifolds can intersect transversely in this 3D level set. Okay, so those are the things we're interested in ejections from one primary that collide with another primary, but it's very nice that we can think of these as intersections, transverse intersections of some manifolds. So here's my collision set for the secondary body, my collision set for the primary body. You imagine flowing, looking at the ejections from the secondary body. Those are things that in forward time hit the secondary body. I look at the collisions for the primary body. Okay, these two things can intersect transversely, and if they do, then I have an orbit, along that intersection, I have an orbit which is ejected from the secondary and which collides with the primary. Okay, but this suggests that what I can kind of do is throw away these tubes and just look for this orbit. So just look for initial conditions that start on the collision set of the secondary body, that we flow forward, and that arrive at the collision set of the primary body. Now, there are going to be some coordinate transformations in between, but this is fundamentally what we're looking for. Okay, so here's kind of a different kind of sketch of that. There's my collision set. You imagine it in the zero energy level of the one of your primaries, you want to flow a little bit, change coordinates, flow again, and now hopefully you're close to collision, change coordinates to the regularization at the other body, flow, and reach that collision set. So this is exactly what we're looking for. And we can write this down as a system of equations that we want to solve. In fact, we can think of it as a zero of a kind of a high-dimensional map. Okay, now there's a complication that kind of makes this all a little bit more interesting. If you kind of count variables and equations here, what you'll see is that this is 20 equations, but in only 19 unknowns. And this is the typical thing that happens when you do boundary value problems, say for periodic orbits in conservative systems. Because of the conservation of energy, you end up with one less variable than you would like. So one way to deal with that, you could try throwing away equations and things like this, but another way to try to deal with it is to introduce an unfolding parameter. So an unfolding parameter is a parameter you would add to one of your vector fields, say the vector field in the original coordinates, that destroys the conservation of energy if it's not equal to 0. Okay? So then you would have that your flow preserves energy along orbits if and only if your alpha is equal to 0. Okay, so you want this to be like a perturbation. So if alpha is equals 0, you want to say you have your original vector field for, say, the circular restricted three-body problem. If alpha is not equal to 0, you want this perturbation to destroy conservation of energy. Okay, let me formalize that a little bit. So let's say I have a smooth vector field and it conserves some scalar function. So I'll say that a vector field G is an additive unfolding for our original vector field F. If I have that this certain integral is not equal to 0 along non-constant solutions of my perturbed vector field. Okay, now what is this really saying? If you think of gradient E gives you the normal vector to the tangent space of the level set of the conserved quantity. So this dot product, gradient E and G, that would be 0 only if G was in the tangent space of your level set. So what you're asking for from this G is that it's sort of always pushing you out of the tangent space. Maybe it's in the tangent space at some point, but not along an open set along an orbit, so that this integral could ever be 0 on a non-constant solution. Okay, so this is my definition of an additive unfolding. Now, it's a theorem that if G is an additive unfolding, and I look at an orbit of the unfolded vector field, then that vector field, an initial point on an orbit and a final point on an orbit, can have the same energy if and only if alpha is equal to 0. Okay, so this is saying that when I have an additive unfolding, I'm moving the energy all the time unless alpha happens to be equal to 0. Okay, so what does this let us do? So I won't prove that little theorem here, just due to time constraints. But let me show you that it's easy to find an unfolding for the circular restricted three-body problem. So here's our vector field, okay, and there's the conserved quantity E. So this is, I'm going to look at the projection, which is just onto the velocity coordinates, okay. I'm going to add that, I'm going to call that my G, and I'm going to take this as an additive unfolding for F. So I'm going to put alpha plus this projection into my vector field F. Now, why does this work? If you look at gradient E dot product with the projection, you can just write down exactly what that is, and you see that it's basically twice the magnitude of the velocity with a minus sign. So if you look at a non-constant solution of this, okay, this can be 0 only if your velocity is 0 along the whole orbit. Well, that can't happen unless you're at an equilibrium. Okay, so this is an unfolding for that vector field. So now let's go back to our problem. What I'm going to do now is replace the flow in the middle coordinate system, the restricted three-body coordinates. I'm going to replace that with the flow but parameterized by alpha. So I'm making that parameter a new variable in my system. And when I do that, I have 20 equations and 20 unknowns. Moreover, okay, suppose I have a 0 of f now. So say I do some computer-assisted proof and I prove I have a 0 of f. Then alpha must actually be equal to 0. Why? Because we know that the Levi-Civitta transformations take the 0 energy level set to the C level set. So this V1 and V2 have to be at energy C, but then you flow from one to the other. So you start and end at the same energy. Alpha has to be 0. Okay, so you're free to find a 0 of this thing, and then you're guaranteed that alpha must be 0 if you did find one. That means you're actually working with the flow you wanted, the restricted three-body flow, and not some perturbation of it. Okay, so this is not an uncommon trick. It's very useful here. Okay, the next question would be, well, are there such orbits? Are there orbits which are ejected from one primary and which arrive at the other? So we need to do some search for these, find numerical candidates for our solution of our boundary value problem. So we run some algorithms here that Shane developed in his PhD thesis that grow these tubes, but way beyond the little picture that I'm showing here. So we grow, very large atlases composed of little polynomial charts for these tubes, and then we look at the atlases for the ejection set and the collision set, and we look for intersections. And doing this, we find here in this picture hundreds, I think this is 115, ejection from the right primary and then colliding at the left primary. So there are lots and lots of these things. So we can say pick one, study this boundary value problem to try to prove the existence. Now, let me just say a few words about how that proof works. So this is one that we proved with mu equals 1/4 at a certain value of energy that we fix. Okay. We use this, so we do this using two standard tools. We use Newton-Kantorovich methods and we use validated integrators. So Newton-Kantorovich or Newton-Kantorovich type theorems, everyone at this workshop is super familiar with. Okay, given an approximate solution of f, we want to conclude there's a true solution nearby. We need an approximate inverse of our derivative, and we need that to be good in kind of a neighborhood. Okay, and then if we have a certain inequality satisfied, we know we have a unique solution in the neighborhood where we made that estimate on the derivative. Moreover, we get that the derivative is invertible at our true solution. Okay. Very standard stuff in here just for finite dimensional maps. So everything can be checked using interval arithmetic, and non-degeneracy is part of the conclusion. But then we prove a nice theorem that says non-degeneracy of the Newton operator implies transversality in the energy level, so we actually get transversality for our intersections of our collision manifolds. Okay, the other thing we need to use to do this, we have to evaluate these flow maps and their derivatives, even derivative with respect to the parameter alpha. For this, we use validated integrators. Actually, we use CAPD, but you can use your favorite validated integrator. Here's some nice references for CAPD. And those are the main things we need, right? If we can evaluate these flow maps and the derivatives with respect to parameters, then we can just do a finite dimensional Newton-Kantorovich on the shooting problem and obtain both the existence of our ejection collision and the transversality. This can be used to do lots of other cool stuff. Periodic orbits that go through collisions, periodic orbits that pass through double collisions, using the stable and unstable manifolds, so the parameterization method that Jean-Philippe discussed. We can study homocliinic orbits. These actually imply the existence of chaos. So there's a lot of nice things to do here. Since my time is kind of up, I'm going to finish up here and just say what I've hoped to talk about was a sort of common framework for talking about a bunch of different kind of things: ejection collisions, heteroclinic, homoclinic orbits, and so on. These can be combined with dynamical forcing, to obtain some very interesting theorems involving collisions. Okay, well, thank you, Akitoshi, for the invitation to speak, and thank you, everyone, for listening. It's been a real pleasure. I look forward to talking with you more.